Hello there, you amazing people. In this particular video, we will be seeing that how can we perform image classification using ANN. So we won't be using any CNN or any other neural network, but instead we will be using just a simple classic neural network, that is artificial neural network, in order to perform image classification on the MNIST dataset. So without wasting any time, let's get started. So first of all, you have to begin by importing your necessary imports. You have to import your TensorFlow, you have to import NumPy, and you have to import your Matplotlib in order to perform some basic plots. After that, you have to perform your step number 2, that is you have to gather and load your dataset. So in order to gather your dataset, you have to simply load the dataset or download the dataset that is already present inside your Keras library. So Keras already has pre-downloaded MNIST dataset available inside it. You just have to load that one. So in order to do that, I'm simply going to write here MNIST is equal to, here MNIST is my, here this MNIST is my variable. So I have to write here tf.keras.dataset.mnist, and then I will be putting this equal to my MNIST variable. So MNIST contains my MNIST dataset. Now I'm going to simply load my dataset. In order to load my dataset, I have to simply use my load underscore data function, and I have to apply this function on my MNIST variable. So what this is going to do is that it is going to create two tuples. So after I perform my load underscore data operation on my this dataset, so what will happen is that I will be receiving two tuples. So the first tuple is going to contain my training dataset, and the second variable and the second tuple is going to contain my testing dataset. So my training dataset is going to contain my training inputs and my training outputs, and my testing dataset is going to contain my testing inputs and my testing outputs. So in order to split my dataset between training and testing, I have to simply use my load underscore data function. Now once you have loaded your dataset, you have to normalize it. So in order to normalize it, I am going to simply divide my training inputs and my testing inputs, that is my x underscore train and my x underscore test, and I'm going to divide it by 255.0 in order to get my floating values. Why I'm going to do that? It is because my inputs contains pixel values from 0 to 255, and so after dividing my 0 to 255 by 255, that is performing this operation, I will be getting my new pixel values between a range of 0 and 1. So because my new pixel values will be of between the range of 0 and 1, which is significantly smaller than the range 0 to 255, therefore while training my model, I will be therefore the training procedure of my model will be significantly fast. So that's why I'm going to divide my training as well as my testing inputs by 255.0. So if you want to print the shape of your data set, I'm going to simply write a print shape of x train and shape of x test. So you can, with the help of this, you can simply see that there is 60,000 and 28 coming. So 60,000 specifies the number of inputs, that is how many different data points are present, and each data point has 20 is of 28 by 28 pixel, that is 28 is my width and 28 is my height. And my training dataset contains about 60,000 images, and my testing dataset contains about 10,000 images. Now we are going to move to our step number 3, that is building a model or instantiating a model. So in order to do that, you have to remember that you have to first define what kind of model you have to use, and then inside that you have to pass your different layers. So the model that I want to use is going to be sequential. By default, you have to use sequential only. So normally, whenever you are creating your model structure is going to look like this, where each and every layer is going to be stacked in front of each other. Here you can see that, suppose this is my layer number 1, this is my layer number 2, this is my layer number 3. Here you can see that my layer number 2 is stacked in front of layer number 1, and layer number 3 is stacked in front of layer number 2 sequentially, and I have to pass input from one side and I will be receiving my output from the other side. So since this has this type of model has sequential nature, which by default most of the models already have, therefore my model type is going to be sequential. Now you can see that each of the layer is densely connected to each other. Also, since each of my layer is densely connected to each other, therefore I have used my dense as my layer type. And also, the purpose of using dense is that you know the step that is forward propagation. If you don't know that, you have to first learn that before you proceed further in the video. So what happens in forward propagation is that you pass input to your neural network. The input gets multiplied to the respective weights, and a bias is added, and after that the whole output, the whole stuff that you receive, is passed inside an activation function, and you will be getting your output. So suppose this is my input, it will be first multiplied by the respective weights, and then a bias will be added. After that, this whole stuff is going to be passed inside a activation function, and I will be receiving this as my this output. So every step contains this particular substep. Therefore, this process is known as forward propagation, and the process of forward propagation is implemented by the dense layer. So I have written here dense, but before dense I have written here flatten. So what flatten does is that it tries to flatten the input that you have given. So my machine learning model, my deep learning model expects some particular type of input. My deep learning model expects that my input is of one dimensional in shape, that is 1D shape. Now, since I'm passing images to my deep learning model, and my images are of shape 28 by 28, that is, my images contain height as well as width. So in order to convert my 28 by 28, that is height into width, into a 1D array, I'm using my flatten operation. So the neural network that I'm going to create contains the first layer as flatten, and then my second layer as dense for forward propagation. Then I have used a dropout layer, and then again a dense layer. So inside the flatten layer, you have to pass your input shape, that is the input that you are feeding to your model, so that it can convert that into a 1D array. Now let us see that what does dropout layer do. So suppose if this is my neural network, generally the neural network that you will be using is not going to be this much small. It contains several layers and several number of hidden neurons per layer. So the training procedure is sometimes sometimes the training takes a lot of time, and also some of the hidden neurons are not that much of importance. It is possible that this neuron might not be that important, that is, the weights of this neuron might not be that important, or this neuron might not be that important. So we use dropout. So since I have specified here dropout and I have passed inside 0.2, so this means that at each and every epoch, my model is going to randomly cancel out 20% of the weights. So if this is my model, so in the first epoch, suppose this neuron is cancelled, that is, out of total number of hidden neurons, 20% of them are going to be cancelled at that step, at each epoch. Suppose at second epoch this neuron might be cancelled, suppose at the next epoch this neuron might be cancelled. So this is the purpose of dropout. So in this way, my machine learning model can check that if suppose this neuron is cancelled, whether it is impacting my accuracy of my deep learning model or not. If it does not impact, then it will simply cancel out that neuron or change the weights, and if it is seriously impacting my accuracy, then it will keep that weight depending upon how it is impacting, that is positive impact or negative impact. So this is the purpose of dropout. After that, I have passed another dense layer, and I have passed here 10. Why 10? It is because my MNIST dataset contains, because I have to make classification, because I have to classify, and the number of categories is 10. You can see that here I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 number of possible classifications that can be made. So the final layer has been so I have decided the final layer to contain 10 hidden neurons, and the activation function is softmax. It is because in most of the cases, whenever you have to perform classification, image classification, therefore you have to use your softmax function, activation function. So remember, whenever you have to perform your image classification or classification related task, so in the last layer you have to majorly use, in most of the cases, use softmax function. So this is all about building your model. Now If you want to see your model summary, you have to simply use dot summary function or dot summary method on your model variable. This will give you the summary, entire summary of your entire architecture of your model. Here you can see that I have first flatten layer, then I have a dense layer, then I have a dropout layer, then I have a final dense layer. And here you can also see the number of parameters at each layer, and a model type is sequential. But if you but in this particular video, since I am using a very basic ANN, therefore I'm not going to summarize at how I'm getting this parameter number of parameters here and this number of parameters here. So because it is not the purpose of this particular video, we will be discussing this when we will be implementing our same model, and when we will be implementing our image classification or any kind of classification or regression problem in deeper models. So I will be discussing the model or summary method in greater detail, that how I arrived at this number of parameters in the later stages. But for now on, the only thing that you need to remember is that, yeah, there is some kind of summary kind of function present, and if I apply that function on my model, then it will give me the summary characteristics of the architecture of my model. So that is all you need to remember right now. Now let us see that how can I compile and train my model. So in order to compile my model, I'm going to simply use my compile method. Then I have to pass my optimizer. The optimizer that I'm going to be using is Adam. Then I have to pass my loss function, which in this case is parse categorical cross entropy. And then you have to pass your metrics. Here I have passed metrics is equal to accuracy. So this will calculate then how often my prediction equal to my labels. After that, I have to simply fit my model. So I have to write here model.fit, pass my training inputs, training outputs, and then my validation data. In a proper scenario, you must split your dataset into training, validation, and then finally testing. But in this case, because MNIST is very common, therefore I have just used my validation data as my testing data also. So this is the these are all the things you need to pass inside your model.fit. And here you can see that I have created a variable which contains my this whole thing. So you will understand the importance of this later. For now on, you should know that this variable will help me whenever you have to plot these kinds of graphs later on, that is loss per iteration graph and accuracy per iteration graph. So if you want to put this, then if you want to plot these, then you can simply pass my model.fit inside a R variable or any kind of variable. But by convention, most people use R, so I have written here R. So after the training is done, you can plot your loss per iteration. In order to do that, you can simply use the plt.plot functionality of my matplotlib, and then I have to pass my R variable, which I got from model.fit step, and then I have to use my history method on that, history function on that. So after, inside the history, I have to pass the metrics that I want to calculate. So I'm going to pass here loss, because I want to first create a graph of loss, and the label is going to be loss. So label will create this stuff that is loss, and with the help of this, I will be getting this kind of plot. If I want to create my validation loss also, that is if I want to plot my validation loss also, so I can comment this out and pass my val underscore loss inside my history, and my label is val underscore loss. And now if I run my code, you can see that my validation loss has also been plotted. Same for accuracy per iteration, you can pass here accuracy, and for validation accuracy, you can pass here val underscore accuracy, and similarly you can change your labels, and you will be getting your accuracy curve like this. Now if you want to evaluate your model, you can simply write your model.evaluate and pass your testing data set. So let us see that at what particular points my model was not able to predict my values correctly. So in order to do that, I am simply going to plot a confusion matrix. Here I am going to provide the code for the same. You can check it out if you want to see how I have plotted my accuracy matrix, because I'm not going to show that here because it will make my video unnecessarily longer. So the code will be provided in the link. You can check it out if you want to see how I have implemented the loss function. So after implementing this thing, I will be getting this kind of plot, that is my confusion matrix. Here you can see that the diagonal elements specifies that cases whenever true label was equal to my predicted label. That is the actual output, the true label, that is the output that has to come, is matching the prediction of my model. So you can see that about 973 times my true label, that is 0, was actually predicted as 0 by my model. About 1125 times my 1 was correctly predicted by my model. About 1009 times my model correctly predicted 2 as my output. And similarly, about 977 times 9 was correctly predicted. But here you can see that when my true label was 9, about 15 times my model predicted it as 4. And similarly, about 7 times my model predicted 9 as 7. And also about 13 times my model predicted 5 as 3. So let us see that why my model did that, so that you can get an idea that why my model predicted these particular values incorrectly. So in order to do that, I'm going to plot those places where my model was not able to correctly predict my outputs. So in order to do that, I'm going to first gather a list of, or an array of, all those indexes where my output values were wrong. So in order to do that, I'm going to write here np.where, and then I'm going to pass those cases where my y underscore test, where my predicted values were not equal to my actual values. And I'm going to gather those particular input value. That's why I've written here 0, and I'm going to store all of these inside my misclassified index variable. After that, I'm going to randomly select any kind of variable, any kind of any index from the list of my index that I got from this step. So I'm going to write here np.random.choice, and I'm going to pass here my misclassified, all the list of all the array of misclassified indexes. And then I'm going to put it equal to my I variable. Now I'm going to simply use my functionality of my matplotlib in order to plot my those inputs where my model was incorrectly predicting my outputs. So I'm going to write here x underscore test and pass my misclassified indexes, and I'm going to pass here cmap as gray in order to get this kind of output. So here you can see that my true label was 5 and my model predicted it as 6. Let me run this code again. Now you can see that the true label was 6 and my model predicted it as 1. That is my true label. The actual label was 6, but my model made a prediction that this looks like 1. And you can see that why my model made an error. It is because this image looks quite like 1, not exactly 1, but it has a little appearance of 1. Let me run this again. Here you can see that my true label was 4 and my model predicted it as 2. It is because if you clearly see this, it is not clear, it is not very clear, and it does not appear truly to be 4. If I run this again, you can see that the true label was 8 and my model predicted as 4. Let me run this again. Here you can see that the true label was 8 and my model predicted as 4. Also, you can guess why it is made, because it kind of looks like 4. Let me run it for the last time. Here you can see that the true label was 3, but my model predicted it as 9. Also, you can guess that why my model did that, so because it kind of looks like 9. So that was all for today, guys. In this video, we learned that how can we perform image classification on the MNIST dataset using simple ANNs. So we didn't use any CNN to solve image classification problem, but instead we used only ANN. We relied on ANN to solve that. We learned that what are the different kinds of inputs you want to do, how to gather and load your data, why you are going to normalize your data, how to load your data, and then then we learned that how can we instantiate or build a model, why I have used sequential model type, and we also saw that why we need to flatten our input, and then we use the why we are using dense layer. It is because dense layer helps us to do the help us in the forward propagation step. Then we learned the purpose of dropout, and then again we saw the use of softmax activation function, and the final layer had about 10 hidden neurons, and we learned the reason behind doing so. And then we learn how to compile a model, and then compile and train a model, and we plotted our loss per iteration graphs, accuracy per iteration graph, and then we saw a confusion matrix in order to see that in what particular cases our model's prediction was wrong and what was the reason behind that. And at last we plotted some of the cases where our model went wrong. So that was all for today, guys. In the next video we'll be performing a regression kind of problem on a simple trigonometric function involving sines and cosines using ANNs. So we won't be using any kind of deeper neural network CNN RN. We will be simply relying on ANNs to solve a regression kind of problem. So we will be meeting in our next video. Until then, bye bye.